Assalamu alaikum. I'm Mustaqim Ahmed Dafat and my ID is 1706173. Here we are presenting the project of Digital Electronic Laboratory and the project title is 4-bit Arithmetic Logic Unit. Our main goal of the project is to implement logical and arithmetic operational circuit which perform addition, subtraction, increment, decrement using only an adder. And finally to observe the output results in 7-segment display in hexadecimal format. Now the questions, what the arithmetic logic unit is. The arithmetic logic unit is that functional part of the digital computer that carries out arithmetic and logic operations on machine words that represent operands. The ALU has mainly two units. One, the arithmetic unit that performs simple addition, subtraction, multiplication, and division. And the other unit is logic unit that performs the logic operations such that and, or, not, etc. In this project, we carried out addition, subtraction, increment, decrement, multiplication, division, XOR operation, 2's complement, AND operation, and OR operation.
Assalamu alaikum. I'm Safa Chaudhary Nirjan, student ID 1706192. Here we are using two tri-state buffers. With tri-state buffer, we are controlling whether bits of B will go or 1 will go. When the enabler of tri-state buffer is kept on low voltage, it works. When the enabler of buffer 1 is kept on low voltage, then the bits of B will go to the XOR gate. We are sending another input to the XOR gate via S2 switch. If S2 is 0, then 0 will go to the input side of XOR gate. So as a result, we will get the exact bits of B at the output of the XOR gate. If S2 equal to 1, then 1's complement will go to the output and will get added to another 1 and will produce the 2's complement of B. It will get added to the bits of A, which will result in the subtraction. When the buffer 2 works, the same thing happens, but the bits that goes to the XOR gate input is 0001 instead of bits of B. The S2 switch will control whether increment or decrement will occur, just the same way I have described previously. Change the slide. Here we can see the multiplication block. Here we have used total 16 AND gates and 3 adders. The bits will get multiplied to one another one after one. The LSB of the first multiplication is taken out of the adder and that is P0. Here P0 equal to A0 into B0. In the same way we get P1 and P2. Here P1 equal to A1 into B0 plus A0 into B1. And P2 equal to A2 into B0 plus A1 into B1 plus A0 into B2. They are all taken out of the adder and are placed at the result of the multiplication one after one from LSB. At the end of the multiplication, we get P7, P6, P5, P4, and P3. Here the technique is very normal with which we are all familiar.
I am 1706193. I am going to describe the division operation of our project. For this operation, we used 4 4-bit full adder and 4 2-to-1 mask. Now, if we look into our block diagram shown here, the adder is performing the subtraction and the connected mask is allowing which output should be passed to the next subtractor. If the dividend is greater than the divisor, the carry out of the adder will be 0, which is our first bit of quotient and also the selector value of the mask. For this case, the mask lifts subtracted value to the next adder. Again, if the reverse case is happened, the first bit of the quotient will be 1 and it is fed into the mask, which allows the previous value to pass through. So the comparison and the other operation is going on like earlier, just only right shifting of 1 bit of the divisor. Likewise, the whole operation is performed and we have got our full quotient with some remainder. If the last carry out of the adder is 1, or we get 0 if the dividend is perfectly divisible. Here, we can also verify the procedure of division by this example included here. The dividend is 1111 divisor is 0, 1, 1, 1, and after the division, the quotient is 0, 0, 1, 0, and the remainder is 0, 0, 0, 1. These results are shown in hexadecimal format in 7-segment display in both software and hardware part.
1706, 172, I will be discussing our logical operations. We performed 4 logical operations and or XOR 2's complement. We were asked to perform the bitwise AND operation of two 4-bit numbers. Thus, we needed only one 7408 IC, which is a quad 2-input AND IC. We will get our outputs from AF0 to AF3 during our simulation later on. For our logical OR, we used only one 7432 IC, which is a quad 2-input OR IC, as we can perform 4 logical ORs in it. We will check our outputs during our simulation. Similarly, we needed a single 7486 IC, which is a quad 2-input XOR IC. We will check the outputs during our simulation. For our 2's complement, we needed a 7483 IC, which is a 4-bit binary full adder, and a 7408 IC, which is a hex inverter. We will get the 1's complement of a given 4-bit number by doing bitwise inversion via 7404 IC. Then we took the 1's complement as inputs in the adder, and the input carry of the adder we will give 1. Thus, the addition of 1's complement and the 1 gives us the 2's complement of a given number. We faced 3 limitations in our project. In our hardware part, we couldn't use a switch due to significant voltage drop in some blocks. We tried using 6-pin push button DPDT switch during our input, but our voltage decreased from plus 5 volt to plus 1.79 volt, and in some cases the IC couldn't receive power due to it. For our display, we used a 7447 decoder instead of a hex decoder. Thus, we couldn't show the result properly if the digit was over 9, and they seems like this. During our simulation of ASID block, we did not consider the carry out, which we will use in the video later.
Assalamu alaikum. Welcome to our software demonstration of our project. We have used three arithmetic blocks and 2 logical blocks. Each blocks are connected to tri-state buffer. If they are all connected to a common segment. 7 segments. So if we want to display the output of a particular block, we will have to enable the corresponding tri-state buffer. So at first we will see the ASID block. It is addition, subtraction, increment, decrement. So if we are now performing the addition operation. For this we will have to put 0, 1, 0 as the switch. So we will have to enable the tri-state buffer, so we can see the result from the 7 segment. So if we want to see the multiplication, we will have to enable the corresponding tri-state buffer, so we can see the result of the multiplication of these 2 bits. So if we want to see the result of division, we will have to enable the corresponding tri-state buffer, so we can also see the result corresponding to it. So we will discuss in details about it in the hardware. Complement. We have used this breadboard to provide supply to specific block. At first, we will provide supply to our addition, subtraction, increment, decrement block. We have performed addition, subtraction, increment, decrement using a single adder IC. So at first, to perform addition, we have to put S2 as 0, S0 as 0, and S1 as 1. So our inputs are 1, 1, 0, 1, and the another input is 1, 0, 0, 1. So we can see that the summation of these 2 numbers are 1, 0, 1, 1, 0. So we can verify it from the LEDs. And we can also verify it from the 7 segment. So if we want to activate the 7 segment, then we will have to turn on the tri-state buffer. Okay. So we can see that our result is 1, 6. We can see that also from our 1, 0, 1, 1, 0. In hexadecimal, we can see that our result is 1, 6.
So for subtraction, we have put the S2 as 1. So we can see that our result is 0, 1, 0, 0. So we can verify it from the LEDs. We have a carry 1, it will be neglected. And we can also verify it from the 7 segment. Answer will be 4. To perform increment, we will have to put S2 as 0, S0 as 1, and S1 as 0. So we can see that our result is 1110. We can verify it from the LED, and we can also verify it from our 7 segment. We got E in hexadecimal, and we also get E in the 7 segment. So for doing the decrement, we will have to put S2 as 1. So we can see that the result is 1100. We can verify it from the LED, and if we take the hexadecimal, we can see that the result is C. We can verify it from the 7 segment display. To perform multiplication, we will have to provide supply to the multiplication block. At first, we have provided input 1010 and 1011. So we can verify it from the LED that our result matches 0, 110, then 1110. So to verify it from our 7 segment, we will have to turn on the respective tri-state buffer from here. So we can see that our result matches with the 7 segment. Our result is 6E.
I'm 1706193. We move to our division block here. Here we see our dividend is denoted by A, and it is in 1011, and our divisor is denoted by B. It is in 0010. If we look into our result, it is shown here 0101 in the calculator, and we can clarify it from our result block. It is 0101, and our remainder is shown here 0001. So if we move to our 7 segment display, it is shown here the result is 5, the question, in the first 7 segment, and the remainder is shown in the second segment.
I am roll 172, and I will be shifting to logical XOR gate. Our input is 1011 XOR 0111, and our output will be 1100. And from the circuit we can see that the output is 1100, and the hexadecimal value of 1100 will be C. From our 7 segment display, we can see that our output is C. Here we are moving to our second logical circuit, OR circuit, and now we are taking input 1001 or 1011, and our output will be 1011. Here we can see that our output is 1011, and the hexadecimal value of 1011 is B. And from the hexadecimal 7 segment display, we can see that the output is B. Here we have our third logical circuit, AND circuit, and our input will be 1110 and 1000, and our output should be 1000. From our circuit we can see that our output is 1000, and our hexadecimal value will be 8, and our 7 segment display says the value is 8.
Now we will perform the 2's complement. We have used the input 1000, so our 2's complement will be 1100. So we can verify it from our LED 1100. Then the result of the 7 segment should be C, and we can verify it from the 7 segment.